Okay, chapter 13 is about weather forecasting, and our driving question is, what is the process involved in making a scientific forecast of the weather? The importance of weather forecasts really depends on what your area of interest is. For example, if you know there's some potential for severe weather, you probably want to protect you and your family's safety and property, so you're going to pay attention to weather warnings. If you are in the agricultural business, then paying attention to longer range temperature and precipitation forecasts will be important to knowing how the crop season will look. If you're in aviation, which many of you are, it's important to know what the winds and the front situations are so you can plan accordingly. For the shipping industry, where they're shipping products across the oceans, it's important to know where tropical storms are. Basically, when you forecast the weather, the steps are like this. First, you gather surface data, surface observations. Next, you gather upper air observations about what's happening with the atmosphere higher up. And then you take your data and you construct surface and upper air maps. And we have computer models that you can plug this data into, and from that you make your forecasts. The agency of the U.S. government that's responsible for all of this is the National Oceanic and Atmospheric Agency, NOAA, of which the National Weather Service is a branch. So how do we acquire the weather data? Well, we have a network of stations across the U.S. that are operated by the National Weather Service, and also from other governmental agencies like the FAA, the Federal Aviation Administration, as well as private citizens and businesses. We also have automated stations that are located in unmanned locations, like the National Data Buoy Center. You can see the picture here in the top shows an ocean buoy that's outfitted with sensors for monitoring weather conditions. And there's no person out there overseeing it. It's just automated, and the data are sent back to the National Weather Service. So the surface weather observations coming from the National Weather Service come from the Automated Surface Observation System, or ASOS, as we've talked about a little bit throughout the course. You've read about it in the textbook. And it used to be that these stations required human interaction to read things like the high temperature of the day or the low temperature, how much precipitation was in the bucket, and so on. But in the 90s, this was all modernized, and it's all made to be automated now. So these stations work continuously, and they report temperature, pressure, wind, precipitation, visibility, obstruction to vision, and current weather and sky conditions, all just through automated observations. There's another system similar to this. The only difference is that it's not necessarily run by the National Weather Service. Some of it's FAA, and then there's a whole lot of these stations that are non-federal. These are called the Automated Weather Observation System. Again, they're automated. It's just under a different jurisdiction because it's not collected by the National Weather Service directly. And then there's the National Weather Service Cooperative Observer Network. These are volunteers who maybe have their own weather instrumentation set up, and their setup has been inspected, and it's part of the network, so the data is good data. Or it could be an organization that has done the same thing. So these are volunteers, they're not paid for this, and it's pretty simple data. It's usually just daily precipitation and temperature readings. Once all of this ground data is collected, it is put onto a chart, and we have a special way to depict it. We have the weather station model, which we've learned about in our labs in this class, that shows the location with the dot on the map of where the weather's coming from, the weather station. It shows the wind direction and wind speed. It shows the temperature. It shows the barometric pressure. And there's a lot of other information that may or may not be included on the weather station model. This little graphic shows the position of where different information would be located if it is available. And then once we take all of the different weather station models for all the places that have collected surface observations, we can put together a surface weather map like you see in this slide. A surface weather map shows the isobars at 4 millibar ranges. So every 4 millibars we have isobars that allows us to see the tendencies, so the centers of low pressure and high pressure, and kind of get a feel for what's happening with winds as they relate to pressure. So we can get a lot of information just from the surface weather map. And on this surface weather map you see there's some radar that's been overlain here, so we can see that the precipitation in this case is right along this frontal boundary. Some more precipitation over in this area. You can see the surface fronts have been drawn in, the cold fronts, warm fronts, stationary fronts, and occluded fronts that we talked about in a previous chapter. In addition to surface observations, we also have upper air observations, and these are collected primarily with radiosondes. Again, we've talked about these throughout the course. A radiosonde is a little radio-equipped instrument package that's tied to a big weather balloon. So there's a little instrumentation package here with temperature and pressure settings, or sensors rather, and a GPS chip so that it can be tracked using GPS. And we have these different locations in the United States from where we launch these radiosondes at specific times during the day. And as they make their way up to the upper levels of the atmosphere, we can get a sense of what's going on up there, specifically in terms of pressure and temperature. And then we can draw an upper air chart, like the one you see in this picture. So with upper air weather maps, instead of looking at a common height surface like we do with the Earth's surface, we have a surface, we normalize everything to sea level pressure, and we can compare what's going on with pressure and so on. But for the upper atmosphere, because these radiosondes don't always reach the same height, it's kind of hard to know exactly where they go, but they are recording pressure. We do what's called a constant pressure surface. So you can see in the label of this chart, it's a 500 millibar constant pressure surface. So what we're seeing here are red lines that represent the isotherms. These are the temperatures of the 500 millibar level of the atmosphere. So it's high up in the atmosphere, but exactly how high we'd have to read the chart for. So we have these other isolines, the blue isolines, that are showing the altitude or the elevation of where this 500 millibar pressure was encountered. So instead of looking at the pressure lines, we kind of look at the height lines. It's a little bit different, but we can see the much stronger wind speeds up here because we're out of the friction layer, away from the boundary layer, and up higher in the atmosphere where the winds can blow faster. And we can see the temperature patterns and the tendency of what's happening higher up in the atmosphere. And typically what's happening higher in the atmosphere dictates what's going to happen on the surface. So other types of forecasts, we have something called a hydrometeorological prediction center. There's an organization within NOAA, it's the Hydrometeorological Prediction Center, that issues short-range forecasts on the order of 12 to 48 hours. I'll include the link in the extra links. And the Climate Prediction Center, also within NOAA, that generates monthly, seasonal, and longer-term outlooks. In terms of short-term weather forecasting, there are many different types of models. You can read about some of these in the textbook, and here I'm focusing on 3 of them: the persistence model, the climatological model, and the steady-state model. So first one is the persistence forecast, which basically says that future weather in the near future will be the same as the present weather. So for example, if it's 86 degrees as a maximum temperature in Prescott today, and a minimum of 60 degrees and it's a sunny day, then a persistence forecast will say tomorrow's going to be the same. So persistence forecasting works well for stagnant weather patterns when things really aren't changing much. So it's easy to predict the future. It's just going to be very similar to today. Another weather forecasting technique for the short term is the climatological model. And this is a forecast that's based on the mean climate for a particular location. So what is a mean? Well, the NCDC, the National Climate Data Center, keeps track of 30-year averages for particular weather variables, so for locations. So for example, for Prescott, let's say the maximum temperature. We can talk about the normal or the mean maximum temperature for Prescott for a particular day or month by looking at what the past 30 years for that location and that weather variable have been. So the National Climate Data Center averages together all of the maximum temperatures for a particular day or month or whatever the variable is, and over a 30-year period you can average those together and it gives you what's called the normal. And so we compare things to normal. We say the temperature is above normal, precipitation is below normal, and so on. That normal is a 30-year average for a particular location. So for Prescott today, maybe the normal is a maximum of 89 degrees Fahrenheit and the minimum is 62 degrees Fahrenheit. These are the normals. And so again, similar to the persistence model, we can say the following days are going to have similar numbers, just based on what's normal. And then the third one I'll talk about here is called the steady state forecasting technique. It's good for analyzing trends, and this technique basically says that surface weather systems continue to move at about the same speed and direction for several days. So if you observe the past behavior for, say, a low pressure system over the past day to 3 days, then it's easier to predict what that system is going to do for the next day or two, and you can predict weather from that. So this uses upper airflow to predict the direction of systems. It's really those upper winds that dictate the direction of these larger systems, like a low pressure system. So by looking at the upper air winds, we can kind of get a sense of what the storm is going to do down on the surface. Here's a weather map, a forecasting map for a tropical cyclone. And with these guys, we are predicting the track as well as the intensity. So the forecasts are usually issued every 6 hours up to 72, 96, and 120 hours. And the tracks are based on various different types of models and forecasts. So they kind of look at what the storm has done. So we see actual data for the storm in the white connected with the solid lines. And then based on what it's done, as well as what's happening higher up in the atmosphere, the models estimate what it's going to do. And so you see here the dashed line is the predicted path that this hurricane is going to take. This particular hurricane was Tropical Storm Gustav, not a hurricane but a tropical storm from 2008. And you see the white polygon around here, which kind of shows the area of probability. So it really is this whole area within here that can be affected, and the storm may move around a bit. But the path that's charted here is what what NOAA has estimated to be the most likely path of this tropical storm. And then once they get the data, once time has passed and we have more data, we know where the storm actually went, they continue to chart it further along its predicted path. So once NOAA has come up with these charts and maps, the National Centers for Environmental Prediction transmit these to local National Weather Service forecast office, and then the local meteorologists use these maps and charts to help prepare their local forecast. And once those forecasts have been determined and made up, that information is distributed to the public through radio, through television, through the internet. If there's hazardous weather on the horizon, we have a series of different statements that come out, beginning with an outlook. An outlook is just giving some advanced notice of, there's a hurricane on the horizon, whatever. And then if it escalates to become a more imminent threat for an area, it becomes a watch, which means that hazardous weather is possible based on current or anticipated conditions. So a watch is just saying it's possible. The next step up is an advisory, which is when we anticipate hazardous weather. It's less serious than a warning, but more serious than a watch. And then finally, a warning is issued if hazardous weather is occurring in the region or it's imminent for your area. So if a warning has been issued, it means a storm or whatever has been observed in your area. The National Weather Service also issues tornado warnings, heavy snow warnings, blizzard warnings, flash flood watches, and flash flood warnings. You'll hear a lot of these flash flood watches, hopefully not too many warnings, during monsoon season here in the desert Southwest. So be sure to read the textbook, and I'll talk to you again soon. Bye for now.